Energy on the move. Everybody knows that a cup of too hot cocoa can be cooled to sipping temperature by adding a splash of cold milk. When you mix cold milk and hot cocoa, what happens to the cold milk? And what happens to the hot cocoa? After mixing, the cup of cocoa is warm throughout. It is cooler than the hot cocoa and hotter than the cold milk. It seems as if the hot cocoa gets colder and the cold milk gets hotter. The new temperature is between the starting temperature of the cocoa and the milk. How does that happen? Kinetic energy equals heat. Objects in motion have kinetic energy. Particles that make up substances are objects. Particles are always moving. Therefore, the particles that make up the hot cocoa and the cold milk have kinetic energy. The amount of energy a particle has depends on how fast it is moving. Faster moving particles have more energy. Slower moving particles have less energy. The particles in hot substances have more kinetic energy than the particles in cold substances. The simple rule is that the more kinetic energy the particles have, the hotter the substance is. This is important. Kinetic energy of particles is directly related to heat. Changing kinetic energy. Energy is conserved. That simply means that energy is never destroyed or created during interactions. The amount of energy in a system is always the same, but it can move from place to place. When energy moves from one place to another, it is called an energy transfer. Energy transfer happens when particles collide. When a fast-moving particle hits a slow-moving particle, the slow-moving particle speeds up. The fast-moving particle slows down. When a particle speeds up, it has more kinetic energy. When a particle slows down, it has less kinetic energy. Energy transfers from a fast-moving particle to a slow-moving particle at the moment of impact. Visualize this situation. 1. Fast-moving particle 1 is on a collision course with slow-moving particle 2, as seen right here in picture 1. Number 2. The particles collide. At that moment of impact, energy transfers from particle 1 to particle 2. As a result, particle 1 has less kinetic energy, and particle 2 has more kinetic energy, as seen right here in number 2. Number 3. The two particles are now moving at about the same speed. Energy transferred from particle 1 to particle 2 at the moment of impact. There you can see the two particles now move at the same speed. If you add up the kinetic energy of the two particles before the collision, it is exactly the same as the kinetic energy of the two particles after the collision. No kinetic energy is created or lost as a result of the collision. The energy of the two particle systems is conserved. But something did change. As a result of the collision, particle 1 has less kinetic energy, and particle 2 has more kinetic energy. The collision resulted in an energy transfer. Energy transferred from particle 1 to particle 2. Energy transfer in cocoa. The kinetic energy of the particles in hot cocoa is high. They are all moving fast. The kinetic energy of the particles in cold milk is low. They are all moving slowly. When you pour cold milk into hot cocoa, the milk and cocoa particles start to collide. When a high-energy cocoa particle hits a low-energy milk particle, energy transfers. The cocoa particles slow down, and the cup of cocoa cools down. Look at the illustration on page 33. Can you tell which of the particles represent a cocoa particle and which represents a milk particle? And can you see how the energy transfer reduce the speed of the cocoa particle? See how the cocoa particle reduced the speed when it hit the milk particle? Remember, reduced particle speed means less kinetic energy. Lower kinetic energy means lower temperature. Using a thermometer. You can use a thermometer to find out if your cocoa is too hot. When you dip a thermometer in that cup of hot cocoa, it reads 90 degrees Celsius. Whoa, too hot. Need to add some cold milk. Move the thermometer over to the cold milk, and the thermometer reads 10 degrees Celsius. That should do the job. But how does the thermometer know that the cocoa is 90 degrees and the milk is 10 degrees Celsius? Kinetic energy. The thermometer reports the average kinetic energy of the particles in a substance. That's what temperature is. Average kinetic energy of particles. How exactly does the thermometer work? Now that we have an idea of how energy transfers takes place, let's put the thermometer into the 90 degrees Celsius cocoa. The cocoa particles collide with the glass particles on the outside of the thermometer stem. The cocoa particles are in red and the glass particles are in green. Energy transfers from cocoa particles to glass particles. The glass particles gain kinetic energy and start vibrating more rapidly. The glass particles transfer energy to their neighbors, and those transfer energy to their neighbors. Transfer of energy from particle to particle by contact is called conduction. Pretty soon, the whole glass stem is at 90 degrees Celsius. The rapidly vibrating glass particles that are in contact with the alcohol inside the thermometer stem transfer kinetic energy to the alcohol particles. Kinetic energy is conducted from alcohol particles to alcohol particle. Energy transfers from glass particles to the alcohol particles. The alcohol expands. So right here we have the cocoa particles hitting the glass particles, and then the glass particles hitting the alcohol particles of what's inside the thermometer. It's transferring energy in this direction. Soon, all the alcohol particles are moving faster, pushing on each other more often and with greater force. The distance between particles increases, and the alcohol expands. As the alcohol expands, its volume increases. Alcohol pushes up the stem of the thermometer. The greater the kinetic energy of the alcohol particles, the more the alcohol expands. Energy transfers to the alcohol until the average kinetic energy of the alcohol particles is the same as the average kinetic energy of the cocoa particles. When this happens, the top of the alcohol is at 90 degrees Celsius mark. This thermometer shows what it would look like in 90 degrees Celsius cocoa. The alcohol rises to the 90 degrees Celsius mark on the thermometer. This thermometer shows what it looks like in 10 degrees Celsius milk. The alcohol rises to the 10 degrees Celsius mark on the thermometer. Put the thermometer into the 10 degrees Celsius milk. Now energy transfers from the outside of the glass thermometer stem to the milk. Energy transfers from glass particles, lowering the kinetic energy of all the glass particles. When alcohol particles collide with lower energy glass particles, energy flows from the alcohol to the glass. The alcohol loses kinetic energy and contracts. When the average kinetic energy of the alcohol particles is the same as the average kinetic energy of the milk particles, the alcohol level is at the 10 degrees Celsius mark, as seen right here. Energy flows from high to low. When two particles collide, is it possible for the fast-moving particle to end up going even faster? Can energy transfer from a lower energy particle to a higher energy particle? No. It never happens. Energy always transfers from a faster moving particle to a slower moving particle of the same size. As a result of an energy transfer collision, the particle that was going faster before the collision will always be going slower after the collision. And the particle that was going slower before the collision will be going faster after the collision. Always. It is sometimes useful to think of energy as flowing. Energy always flows from higher to lower, from hot to less hot or cold. When does energy stop flowing? When you pour cold milk into hot cocoa, the high-energy cocoa particles and the low-energy milk particles instantly mix with one another. They collide with each other billions of times every second. The energy flows from the high-energy cocoa particles to the low-energy milk particles. Almost instantly, the average kinetic energy of the milk particles is the same as the average kinetic energy of the cocoa particles. The kinetic energy level is uniform throughout, lower than the cocoa and higher than the milk. Has the energy stopped flowing? Has energy transfer between particles stopped? No, not really. Even when the average kinetic energy of the mixture stays steady, there are still individual particles that have high energy, and there are particles that have low energy. But the number of high-energy particles is the same as the number of low-energy particles. When the temperature is constant, the system is in a condition called equilibrium. At equilibrium, there is no change of temperature. Think of it like saying equal. It's all equal. When a mixture of hot cocoa and cold milk has reached equilibrium, you can use a thermometer to measure the equilibrium temperature. The equilibrium temperature is a measure of the average kinetic energy of all the particles in the system. This includes the cup, the mixture of cocoa and milk, and the thermometer. So, has the energy stopped flowing? Think about this. The phone rings and you talk to a friend for 20 minutes. Now the cup of cocoa is cold. Why? The room is cooler than the cocoa. Particles of air collide with the cup and the surface of the cocoa. Energy transfers from the cup of cocoa to the air. Energy continues to transfer to the air until the average kinetic energy of the cocoa is the same as the average kinetic energy of the air. We say the cocoa is room temperature. The cocoa is at equilibrium with everything else in the room. Energy transfer summary. All matter is made of tiny particles that are too small to see. The particles are in constant motion. Objects in motion have kinetic energy. Particles are objects in motion, so they have kinetic energy. The faster a particle moves, the more kinetic energy it has. Kinetic energy is related to heat. The faster the particles in a substance move, the hotter it is. Energy can move or transfer from one particle to another when particles collide. Energy always transfers from higher energy particles to a lower energy particle. The transfer of kinetic energy from particle to particle as a result of contact is called conduction. Temperature is a measure of the average kinetic energy of the particles in a mass. Matter heats up and cools down because of energy transfer at the particle level. Review questions. Explain how cold milk cools hot cocoa. Number 2. Why do you think an ice cube feels cold when you hold it in your hand? Question 3. What will happen to a balloon stretched over the mouth of this empty bottle when the bottle is placed in hot water? Explain all the energy transfers. Number 4. When does energy flow from a cold object to a hot object? And 5. What does the thermometer measure and how does it do it?